Hi, Ben. Looks like you're the only one in there. Hey, Christian. Hey, Caleb. Hey, James. Hey, Kellen.
Hello.
All right, well, I'm going to go. Uh-oh, your internet connection is unstable. That's not good. Oh, I still seem to be connected, so just leave that there. Okay, we're going to cover section 3 today, and we're going to be looking at the domain again, but of rational functions. And then we're going to look at something called asymptotes, vertical asymptotes, horizontal asymptotes, and oblique asymptotes of a rational function. So first, I'm just going to define what a rational function is. And basically, it's a fraction where you have an x in the denominator. You don't necessarily have to have an x in the numerator, but it says a rational function is a function of the form r of x equals p of x over q of x, where p and q are polynomial functions, and q, which is the denominator, is not the zero polynomial, meaning it's just a constant. So you could have like 3 over an x plus 2, or you could have an, whoa, a little thick. Or you could have like an x plus 5 over an x minus 6. But you can't have like an x plus 3 over a 7. This is not a rational function. Because it says Q is not a zero polynomial. 7 is a zero polynomial. Its degree is 0. Because that's like saying 7x to the 0. So you're looking for junk that looks like this, or looks like that, or anything that's got x's definitely in the denominator. Okay? So it's going to be a fractional mess. Sometimes they're really nasty, and sometimes they're not so much. Okay, so let's find the domain of a rational function. They have given me 1, 2, 3, 4 different examples, and they also put the answer right there with it. So we're looking at find the domain of this function right here. And then they give you the answer right after it. It is the set of all real numbers except for -5. That's because your denominator right here, x plus 5, remember, when you're in fraction land, denominators are not allowed to equal 0. So the x plus 5 cannot equal 0. And if I solve that for x, I would just be subtracting 5. So x cannot equal -5. And then they put that down here in set builder notation. It's the domain is the set of all x. The set, remember, braces mean the set of all x. And then this line right here, which I'm highlighting in green, means such that x cannot equal a -5. X can be any other number in the world but -5. Okay, so then on part B, our denominator is a little bit more complicated. It's an x squared minus 4. So they're going to take that x squared minus 4, this right here, and they went ahead and factored it. And then they're like, okay, x plus 2 and x minus 2. X squared minus 4 is the difference of two squares. It factors into conjugates. And then neither one of those are allowed to equal 0. So if x plus 2 is not allowed to equal 0, when you subtract 2, you'd get x is not allowed to equal a -2. And then the x minus 2, you do the same thing. X minus 2 is not allowed to equal 0. Solving for x, I would add 2 to both sides, so x can't be 2. And here it is in set builder notation. It's the set of x such that x is not allowed to equal -2 and x is not allowed to equal +2. I think in my math lab, you're just going to have to type in -2, +2, but we'll look at that. All right, now when we get to part C, C has a denominator of x squared plus 1. Now, if you say, okay, x squared plus 1 is not allowed to equal 0, and then the next step would be subtract 1 from both sides, you'd say that x squared is not allowed to equal -1. And then if you try to square root to solve for x, guess what? You have just gone to imaginary land, which means there is no number that will ever cause the denominator to equal 0. Remember, the square root of -1 is equal to I. It's imaginary. So they're saying right here, it is the set of all real numbers, because there is no number that will ever cause the denominator to be a 0. Therefore, every number is in the domain. Every last number. And then the last one, the denominator is just an x minus 1. So obviously, x is not allowed to equal +1, because 1 minus 1 would give you 0. So basically, you just take the denominator, say, hey, it's not allowed to equal 0, and then solve it for x to figure out all the numbers it's not allowed to be. So at this point, I went to my math lab. And this is number 4. It says find the domain of the following rational function. So you are going to simply take the denominator, each piece, and say, well, x minus 5 is not allowed to equal 0. And also the x plus 2 is not allowed to be 0. Here I'd have to add 5 to both sides. And over here, I'd have to subtract 2 to both sides. Cancel, cancel. So over here, x is not allowed to equal 5. And over here, x is not allowed to equal 0 minus 2 is a -2. That was a 0. My zeros are not looking too
April, would you explain?
Yes.
Hey, April, would you explain why x plus 5 over 7 is not considered a rational function? You're going in and out, and I missed it.
X plus 5 over 7. Where was that?
First slide.
This one here?
Yes.
The x plus 3 over 7? Because the denominator, q, this is q right here, q of x. The function q cannot be a 0 polynomial. And since your denominator is a 7, that's the same thing as 7x to the 0. So that is a 0 polynomial. So therefore, it's not a polynomial function.
Thank you.
Okay. Yeah, my phone, I'm on my hotspot because the Wi-Fi here, I'm at my son's house, isn't the greatest, and I was afraid it would kick off. I think he needs a new modem. So I'm using my hotspot, but it keeps showing up as it's not stable. So I hope you're getting all this. Okay, so I was on number 4. Okay, so for my math lab, it is saying type an inequality, use integers or fractions for any numbers, blah, blah, blah. Use a comma to separate answers as needed. All right, so it's going to be choice A, and it says the domain of h of x is, they already have the braces, they already have the x and the such that, but what you have to type in is x is not allowed to equal, and then I'm going to put them in numerical order, -2, 5. And my math lab will take it like that. I know in their examples, they wrote it as 2 separate problems. X does not equal -2, x does not equal 5. But when I typed it in, it took it both ways. And then I went ahead and did number 5. Now 5 is not simplified for me. So I'm going to take the denominator, and the 4 doesn't have an x with it. So you just kind of ignore him. But then you're going to take this x squared minus 64. And that is not allowed to equal 0. And I can factor that because that is a difference of 2 squares. The x squared will be x and x. And then 64 will be 8 and 8. And then one of these has to be a plus and the other one has to be a minus. That's because there's no middle term. You just got the x squared and you got the minus 64, but there's no middle x guy. That's because your negative 8x for outsides and your positive 8x for insides cancels out. So there was no middle term. So either you're going to say the x plus 8 is not allowed to be 0, and the x minus 8 is not allowed to be 0. And then subtract 8 on this one and add 8 on this one in order to solve for x. That cancels. So x not allowed to be a negative 8. And over here, x is not allowed to be a positive 8. And just make sure when you click on choice A, they've got the set of x such that, but you have to type in the x right here. Then there'll be a toolbox at the bottom when you click on your box. And in that toolbox, you'll see, it'll be down here at the bottom, there'll be a choice that is a, you know, a not equal to symbol. And then type in your numbers separated by commas. Okay, so that goes over the domain stuff. We are now going to start looking at what the heck an asymptote is. So they start with an example of y equals 1 over x squared. Now, just to refresh your memory, we did a graph of y equals 1 over x to the first power. And when we graphed it, it looks something like this, where part of it was in quadrant 1, and then its mirror reflection was down in quadrant 3. That's because this was an odd function, and it was symmetric around the origin, or as I like to call it, it's a double fold. If you folded this thing in half vertically around the y-axis, and then you fold it again horizontally around the x-axis, this part right here would ultimately land on this part right there. Now, if you look at this function, which is y equals 1 over x squared, this is an even function. Y equals 1 over x squared. And if you look at the graph, you still have this guy, which is in the first quadrant, but what you're going to have is a mirror image of him in the second quadrant, because it's an even function, so it'll be symmetric around the y-axis. So it's almost like this guy here flips up and goes into quadrant number 2, like that. And they did some plugging and chugging. You know, they plugged in x is 1/2, x is 1 over 100, x is 1 over 10,000, x is 1, x is 2, x is 100, x is 10, just to show you that what's happening is as you are getting closer and closer to 0, your graph gets closer and closer to the y-axis. Let me erase this yellow stuff. Okay, so when x was 1/2, let me do this. When x was 1/2, you got a y coordinate of 4. Okay, that was this point right here. Okay. When we made x a lot smaller, when x is 1 over 100, when you plug 1 over 100 where x is, you have 1 divided by 1 over 100 squared. Trust me, when I'm done with it, you get 10,000, okay? So when x is 1 over 100, which 1 over 100 would be like really close right here, then it is way the heck, the point would be way the heck up here somewhere. And then they get even smaller. They go to the next one and they do 1 over 10,000, which makes y even bigger. So now we're getting even closer to the origin. I'm getting microscopically close to x being a 0. And the y is huge. So it's way up here now. I mean, way, way up there. And what happens is, as you keep getting smaller and smaller and smaller and smaller, which they didn't, they stopped at 1 over 10,000. And then they said, hey, let's go in the other direction. Let's go with 1 and then 2 and then 100. And if you look at what's happening there, 1 gives you 1. 2 gives you a 1/4. 100 gives you 1 over 10,000. 10,000 gives you 1 over 100 million. Now, as x is getting bigger, y is getting smaller. And when I'm looking at these now, let's see, I'll go back to yellow. When I have x is 1, y is 1, that's this point right here, right? 1, 1. When I have x is 2 and y is 1/4, that's this point right here. When you get to 100, you get 1 over 10,000. So now if x is 100, which will be way over here, I can't even see it on this graph because my x-axis goes to 3 right here. We're looking for 100, which is way down there. It's getting really, really tiny. It's getting really, really close to the x-axis. So in this picture, as the graph is getting closer and closer to the y-axis, it never actually touches it. And when x gets bigger and bigger, then y gets closer and closer, to the x-axis, but it also never touches it. The line that they get close to but never touch is called an asymptote. It's like this, it's like you can get really close to that line, but don't you dare cross it. They're never going to cross it. And they call those asymptotes. And then this is just an example of using transformations again. And it is a rational function, except now that we've learned about, you know, this graph of 1 over x minus 2 squared, you would start with the basic graph of 1 over x squared. Which would be this. And then you would say, okay, well now I've got that 1 over x squared, but I'm going to bring in this minus 2. So that means it is going to shift 2 to the right. So it's going to go 1, 2. So right now, my y-axis is technically the vertical asymptote, but now what you're going to have is, use gray for this, you're going to have a new vertical asymptote at 2. And so now my graph has moved 2 to the right. So now it's doing this. And then the last thing I'm going to take a look at is that plus 1. And so I've got the minus 2 here. And so now we're going to look at the plus 1 right here. And all that's going to do is move my graph up 1, right? It's going to shift it up 1. So here's still that vertical asymptote. But now where I had the x-axis as my horizontal asymptote, this thing moves up 1. So now you've got your new asymptote right here. And they'll show it with dotted lines. All right. Dotted lines are like these imaginary lines. And now my graph is looking something like this. Sorry, it's just a sketch. And then they show that on the next slide. So they started with the blue, y equals 1 over x squared. And then they did what I did and they added in the -2. You can see that shifted 2 to the right. And then they added in the +1, which shifted it up 1. But you can see they've added dashed lines as the asymptotes, because it's no longer the x and y axis that it's approaching. It's now approaching that vertical line of x is equal to 2. Remember, all vertical lines are always x is equal to wherever it's crossing the x-axis, which in this case is right here at 2. And then the horizontal asymptote would be wherever it's crossing the y-axis, which was y equals 1. All right. So that's just an example of asymptotes. And then here's just another slide they threw in here. Again, it's showing you that what we're looking at here is as x is getting bigger, you're going from 10 to 100 to 1,000 to 10,000. I can see it's going from 1.0156 to 1.001 to 1.00001 to a whole bunch of O's and a 1. It's getting closer. I can look at this and say, as x gets larger, y gets closer. Again, it's saying my internet is unstable. What do you want? I'm teaching a class. Gets closer to 1. No, there's people out there. Sorry, I'm having a conversation with my son right now. There's people at home listening to me.
Oh,
yeah.
I might start mowing the grass here in a minute. I don't mean for it to
Just stay over on that side of the house.
What?
All right. The next one, we're going from, if you're looking at these numbers, you're going from -10 to -100 to -1,000. Okay, x is getting smaller here. Because remember, the more negative you are, the smaller you are. Ooh, words to live by. Okay, and again, I see 1.0069, 1.0001, 1.001, 1.001. Again, as x gets, why did I write larger? I don't know. Sorry, my son messed my head up. As x gets smaller, y gets closer to 1. Okay, now the next two look a little different. This time we're looking at x is actually going from 1.5 to 1.9 to 1.99 to 1.999 to 1.99999. Now I'm saying as x gets closer to, if you keep going 1.9999999, aren't you actually getting closer and closer to the number 2? Okay, so as x gets closer to 2, now I'm looking at my y's. The y coordinate is a 5, then a 101, then a 10,001. As x gets closer to 2, y gets larger. And it actually gets large fast. It's getting larger and closer to infinity. That's what you could actually say in all of these. If I went back to the first one, I could say as x gets larger and closer to infinity, y gets closer to 1. Now in the next one, I would say as x gets smaller or closer to negative infinity. All right, and then that last one down there, x is going from 2.5 to 2.1 to 2.01 to 2.001 to 2.00001. That was my Beyonce impression. Did you like that? Wait, is that Beyonce? Yeah, that's Beyonce. As x gets closer.
That's a good one.
This works so much better in the classroom when I can see your all's faces. I have no idea if you're rolling your eyes or smiling. Let's see. As x gets closer to 2, then my y's go from 5 to 101. They're actually getting larger and larger and closer to infinity. Gets closer to infinity. That's just like looking at the numbers and saying, what's happening here? I can see what's happening. So they tried to take this and put it into math speak with a definition. It says, let R denote some function. As x approaches negative infinity or as it approaches positive infinity, the values of R of x approach some fixed number L. And that line y equals L would be a horizontal asymptote. Okay, let me try to point those two out to you. No, go purple. Okay, so as x approaches infinity or negative infinities, let me go back a slide. Which one was in? Again, my internet is unstable. Here we go. Which one's getting closer and closer? Okay, so this one was approaching infinity as x got closer to infinity. And this one, x got closer to negative infinity. Then they both, in both examples, y was getting closer to the number 1. So y equal to 1 is a, and I'm just going to abbreviate HA, horizontal asymptote. It's a horizontal asymptote. But then the other two, it says, as x approaches some number c, okay, then the values of your function either approach negative infinity or positive infinity. And then that means that the line x equals c is a vertical asymptote. So now we're talking about the other two examples on the previous slide. As x approaches some number c, well, in this case, x was getting closer to 2. We're looking at this one here and this one here. They were both getting closer to 2. As x gets closer to 2, that's your c. c is equal to 2. Then the y gets closer and closer to infinity, or, well, in both of those cases, they were positive infinity. So you could have one going to negative infinity. They didn't give you every possible scenario, but just trying to give you a couple of examples. So I'm hoping that explains this obnoxious definition right here, because it's weird. You just read that and you get a headache. You're like, what the hell? But does that help where you look at the numbers and you see what's going on and then apply it to the definition? I hope. Okay, and now these are just some pictures of different asymptotes. The first two are horizontal and the second two are vertical. And it just says as x approaches infinity. So you can see on this first one, as x approaches infinity, see how this line's going like this? It keeps going to the right. So x is getting bigger and bigger and bigger. But the line gets closer and closer to that dotted line. This just keeps running along alongside of it, but never touches it. So y is equal to, and they just use the capital letter L, whatever number that is. If that's 3 on the y-axis, y equals equal to 3. And the same thing on this one, except now as x approaches negative infinity, and you can see it's pointing in the negative infinity direction, it keeps going in that direction, but it'll never pop above that dotted line. So that makes that a horizontal asymptote. It never crosses it. And then this one, now we're looking at as x approaches some number c, because now x is getting closer. It's like it's heading towards this dotted line, but you know, it's like moving along, and then, oh, I can't cross that line. I got to turn. I got to run alongside it. And oh, I got to go up like that. And the same thing over here. It's like running along, then, oh, I got to run alongside it. It's kind of like running alongside a fence, and you can never get over that fence. You can never get through that fence. There's no hole in that fence. You can't get over the fence. Have to run alongside it. And you'll get microscopically close, but you never touch it. So. And then that now has a vertical asymptote, which will be whatever x equals c is. And then sometimes and this would be an even function. And then this last one over here, this one is actually an example of an odd function, because you got one side ending upward and the other side going downward. Right, on the even one, they're both going up, but it's the same thing. It's approaching that dotted line. So now, those are horizontal asymptotes. These two are horizontal asymptotes. And these two are vertical asymptotes. But that's not the only two ways I can draw a line. You can also draw slanted lines, you know, y equals mx plus b. And when you do, those are called oblique asymptotes. And I always got the word oblique confused with opaque, but opaque has to do with glass, and you want your shower doors to be opaque, because if they're not, you can see right through them. All right, just you know, a little extra information for you. Oblique simply means slanted, and it can be a line going uphill, or you could have a line going downhill, positive slope or negative slope. But if it's slanted, it's oblique. It's a slanted, or you could say sloped line. My handwriting's horrendous today. All right, so I've jumped back to my math lab again. This is number 6, and there's 5 questions. First, they want you to find the domain and the range. Then they want any intercepts. And then they want all 3 different types of asymptotes. And you're basically just looking at the picture. It's a lovely picture. Remember, the dotted lines are your asymptotes. So I can see from this picture, I've got a vertical and an oblique, but that's it. But let's start with the domain. Remember, the domain is all of your x's. Now, as far as the domain is concerned, you really only have to look at the vertical asymptote, because the oblique one is actually crossing at the origin, and so is that one. Okay. When I'm looking at this graph, it's, if I look at it from left to right, it's down here somewhere and it's coming up and it's coming up. And what happens is it's going to get closer and closer to this, vertical asymptote, but it'll never cross it. And if it never crosses it, that means that this point right here cannot be in my domain. Now, even though there's another one going here, and this line, you know, runs alongside it like that, there's enough points up here that are associated with all of those X's getting closer and closer and closer to the 0, but not touching it. They're just up here, not down here. And then on the other side, I'll just use a different color for the other side. Over here, it's moving away from this dotted line. But on the other side, or down at the bottom for this dotted line, it gets closer and closer and closer to it from the other side. So it's like on the left, you're getting close to the 0, and on the right, you're getting close to the 0. But from both of those sides, you never cross that 0. So in this little box right here, you have to type X, not allowed to be 0. It's a visual thing. I'm hoping that highlighting it and talking at the same time makes sense. I know you've got that oblique asymptote also, but on the left where the yellow is, it does get really close to the 0. And on the right where the pink is, it's getting close to the 0 on the other side. And they keep going in both directions. This one keeps going that way to positive infinity, and this one going that way will go to negative infinity. So all other X's are accounted for except for 0 on either side. Let's see, that's the domain. Then they want to know what's the range. Now remember, the range is all of your Y coordinates. And this graph on the left, it keeps going up, and it started way down here. And the same thing on the other side. It starts way down here and keeps going up. So as far as the y-axis is concerned, every single point on that graph, whether it's on the yellow part or the pink part, it stretches vertically and down to the bottom. So every number is accounted for, every single number. So on this one, it's a set of all real numbers. You would have to have a horizontal asymptote in order to eliminate a Y value. So your vertical asymptotes remove numbers from the domain, and your horizontal asymptotes remove numbers from your range. Sometimes the oblique does and sometimes it doesn't, but in this case it doesn't because this is on both sides. So, okay. And then I got part B in here. It says find the x-intercepts. So for part B, my x-intercepts would be this point right here and this point right there, which would be -5 and +5. So use a comma to separate. So in this box, -5 and +5. And then they want to know y-intercepts. Well, there are no y-intercepts. Your vertical asymptote is the y-axis. This right here, your graph never touches that, and that is the y-axis. So there are no y-intercepts. None. Nada. Zippo. Okay, and now it wants to know what are the horizontal asymptotes. When I look at this picture, I see no dotted lines. There are none. I see no horizontal dashed lines. So there's no horizontal ones. And next, a vertical asymptote. Yep, got one of those. Vertical asymptote is this guy right here. And that is at x is equal to 0. It's going through the x-axis at 0. And then it wants the oblique ones. Do we have any oblique ones? Oblique means slanted. That would be this one. Ooh, now this one's a little tougher. I have to have an equation for that line. Now, if I go old school on this, that's a line. And lines have the form of y equals mx plus b. B is where it crosses, that's your y-intercept, right? It's crossing the y-axis at 2. So this is a 2. And what I need is the slope. And let me go to a yellow, orangey, whatever. From this point to the point they labeled as 2, 4, I would have to go up 2. No, up 4, sorry. That is up 4 and over 2. Going from one point to the next, I would have to rise up 4 and run over 2 to go from the blue point to the red point. Starting at the blue point, ending at the red point. That would be up 4 over 2, which would be a 2. And they have the y equal to part, so you just have to take the 2x plus 2 and type it in right there. All right, you guys got any questions yet? All right, now number 9 is an example of the 1 over x squared graph, except it's 1 over x minus 4 squared. So keep in mind, you would actually start with 1 over x squared, which would be basically this, right? But then you're going to bring into it, it's now going to be 1 over x, and there's a minus 4 in here. So this thing is going to get shifted 4 to the right. Remember, when it's inside parentheses, it goes right or left, and it's always the opposite of what you see. If I see minus 4, it's got to be a plus 4. So this thing's going to go over 1, 2, 3, 4, which means I now have a vertical asymptote that is right here now. Instead of the y-axis, it's now that guy. And so now my graph looks like this. So looking at my choices, the only one that is shifted to the right is D. And they've labeled it 20 to negative 20, and it looks like 1, 2, yeah, there's 10. So every little hash or every little square in that graph is a unit of 2. So 1, 2 makes 4. So it's D. D, 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 D. Okay. Now it wants to know the domain. Remember, if there is a vertical asymptote, that will be left out. Vertical vertical asymptotes are not in the domain. So in this picture, it was this vertical line is x is equal to 4. So x cannot equal 4. And that would be choice A. Yep, it's only 4 that's left out of that. And then the range, now the range is how this thing looks vertically. And this would be where you have a horizontal asymptote. Horizontal asymptotes are left out of the range. And on this one, my horizontal asymptote is the x-axis, and that has the equation of y equals 0. So y cannot equal 0. And that would be choice. Oh, hang on. Yes, y cannot equal 0, but also on this one, because I have no graph in quadrants 3 or 4, it's only in quadrants. Yep, my graph here is totally in quadrants 1 and 2, right? It's totally in quadrants 1 and 2. So my y keeps going up. It can't equal 0, but it can be anything bigger than 0. But since it's not in quadrants, graph is not in quadrants 3 and 4, so y cannot be less than 0 either. It can't be 0 and it can't be less than 0, so that means it's gotta be greater than 0. So A. My range would be any y coordinate that is greater than 0, because all of the points on my graph are in quadrants 1 and 2, which is where all your y's are positive, greater than 0. Okay. What are the vertical asymptotes? Well, I can see it in the picture. Here's my vertical. Whoops, didn't mean to do that. There's my vertical asymptote right there. Doot. And, oh, whoops, sorry. That says the left vertical and the right vertical. There's not more than one. There's only one. So that should have been choice B. There we go. There is one vertical asymptote, and it is, and you have to type the whole equation in here. All vertical lines are x is equal to wherever it's crossing the x-axis, and it's crossing this at 4. X is equal to 4. And then horizontals, there are none. There are no, oh, I'm sorry, damn it. Yes, there are. What are the horizontal asymptotes? It's right here, which is the x-axis. There is only one horizontal asymptote, and it is a horizontal line that is always y is equal to wherever it's crossing the y-axis, and it's crossing it at 0. And then it asks about oblique, and this is where there are no oblique ones. There are no oblique. There are no slanted lines. Okay. Okay, so I just added this slide in here for a little comic relief. You can laugh at will. Maybe you don't understand the left one, but that's from MC Hammer's Can't Touch This song, you know?
Ha.
Thank you. And I really like the one on the right. Kiss my asymptote, mother function. So inappropriate, but so funny. I actually have a magnet in my office that just says kiss my asymptote on it.
That's
Doesn't say
awesome. I'm
mother
going to have my
function.
eyes removed tomorrow.
What?
I'm going to go have my eyes removed tomorrow.
My eyes, my eyes. All right, so moving on. Okay, now, the last couple examples that we did were pictures. I just had to look at the damn things. I'm like, okay, I see the dotted lines. Yeah. But they're not always going to do that for you. Sometimes they're just going to give you the function and the function only. So, a rational function, r of x, is equal to p of x over q of x. And the important thing is, it has to be in lowest terms. In lowest terms, meaning reduced down. Then it will have a vertical asymptote, x is equal to r, if r is a real zero of the denominator, which is pretty much the same thing as when you were asked to find the domain of your function. Whatever was left out of your domain, that is where vertical asymptotes happen. So when you were asked those questions before we started talking about asymptotes, you were already finding vertical asymptotes. So these four examples here, when I look at x minus 1, there will be a vertical asymptote at x is equal to 1. This one right here, x squared plus 1, if I set that equal to 0, you would get x squared equals -1 and it goes to imaginary land. There are none here, no vertical asymptotes. On this one, I'd have to factor it, x plus 2 and x minus 2. So my vertical asymptotes are at x equals -2 and x is equal to +2. And then this one, I have to factor him to see it, x and x plus 7 and -3. So my vertical asymptotes would be at x equals -7 and x equals +3, which will be the numbers that would be left out of the domain. On the green one, I would simply say all real numbers. There are no, on that graph, nothing would be left out of the domain. And then their next slide, I think, shows all that, yeah. A, f is in lowest terms, blah, 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 blah. Oh, wait a minute. I forgot to reduce that last one, didn't I? Oh, my bad. My bad. I totally forgot the numerator. On, what color did I use? This one, okay. On B, my numerator was just an x, which didn't reduce my fraction. On D here, totally forgot to take the x squared minus 9 and factor that to be x plus 3, x minus 3. And then when I do that, this x minus 3 in the numerator would cancel this x minus 3 in the denominator. So that the only thing I have left in the denominator is x plus 7. So this would be my only asymptote, not that one, sorry. I forgot that part. I even highlighted it up here so I would remember. In lowest terms. Forgot to do it there. Bad teacher. So here's their explanation. Okay, and then this is just showing some examples with multiplicity again, odds and evens. Examples A and B are both odds. C and D are both evens. Those are just examples showing that. Now, finding horizontal or oblique without a picture is much more difficult. There's rules. The vertical ones is simply make sure it's in simplified form, and then whatever is left out of the denominator, that is where your verticals happen. Horizontal and oblique. Oh, okay, here's the rules. All right, rule number 1. If n is less than m, okay, if n is less than m, and when you're looking at it, here is the n and there is the m. They have written the numerator and the denominator, you know where they wrote that a sub n times x to the n plus a sub n minus 1 x to the n minus 1, which is, you know, just PhD double talk in math. Basically what they're saying is it's in descending order. These are in descending order. You know, where the highest exponent is first. So the numerator, the first term shows its degree. N would be its degree. And the denominator, the first term, has its highest exponent. So m is its degree. So they're saying if the degree of the numerator is less than the degree of the denominator, then the line y equals to 0 will always be a horizontal asymptote. So if I gave you the function r of x was equal to an x squared over an x cubed, like x squared plus 5x, and this was x cubed minus 2x squared, blah, 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 like that. When you're looking at it, my n, my numerator's exponent of 2 is less than my denominator's exponent of 3. The degree of the numerator is less than the degree of the denominator. Somehow you got to remember this, write it down. Then y equals to 0, which is actually the x-axis, remember? Y equals 0 is the x-axis. So whatever this graph looks like, I know it'll never cross the x-axis, for sure. Now, number 2, if n equals m, if the degree of the numerator equals the degree of the denominator, then the line y equals whatever a sub n over b sub m is. Basically, you're taking the numbers or the coefficients on your x's, and that is the line where you'll have a horizontal asymptote. So if I gave you r of x is equal to, I don't know, 3x to the 5th over 8x to the 5th, your horizontal asymptote would be y equals the 3/8. But that's only if the degree of the numerator equals the degree of the denominator. Somebody studied this and figured this all out, so they made a list of rules. That'll be another horizontal. Okay. Now, number 3. Orange. If n equals m plus 1 more, if the degree in the numerator is 1 more than the degree of the denominator, then the line y equals ax plus b is an oblique asymptote, which is the quotient found by using long division or factoring. We will be doing the factoring. You do not have any problems in my math lab. Well, you're going to be doing long division. So you don't have to worry about that yet anyway. I did leave an example in their slides that shows it, but we don't have to do it. Ours will be factoring. So that's why I added in my little handprint there, handwriting, or factoring. But if you're looking at an example for this one, it would be the degree of the numerator is 1 more than the degree of the denominator. So if you have an x to the 4th plus blah, 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 that would have to be over an x cubed, you know, and blah, 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 like that. Then your oblique asymptote, what'll happen is we're going to factor it and it'll reduce down to give us the equation of y equals ax plus b. And I've got an example. I'll show you that in a minute. Which brings me to number 4, which says if n is m plus 2 or more, because it says greater than or equal to, if the degree of the numerator is 2 or more greater than the degree of the denominator, then you will have no horizontal or oblique asymptotes. And the end behavior of the graph will resemble the power function of a over b, but x to the n minus m. So an example of this would be if f of x or r of x or whatever the hell of x it is, if I had, let's say an x to the 6, you know, blah, 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 and this was an x to the 2nd, blah, 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 blah. 6 is 4 more than 2, so it is 2 or more greater. Then there are no horizontals. There are no obliques, and then the graph would resemble an x to the 4th. It would have an x to the 4th look. Now there is something important down here at the bottom. It says, note, a rational function will never have both a horizontal and an oblique. It's either one or the other, or neither, because it could have neither, but it can't have both. You can have a horizontal, you can have an oblique, or you can have neither of them, but you will never have both of them. Period. When it comes to horizontals and obliques, you can have a vertical with a horizontal, and you can have a vertical with an oblique, and you can have just a vertical and no horizontal and oblique. Okay, so here's their example. I'm just going to scan through it. You can see that it is where the numerator 4 is, that is equal to 3 plus 1. It's 1 more than the denominator. So it's going to have an oblique asymptote, but you'd have to do long division. And here's the long division, so don't freak out, we're not doing that. I just left it on there. But when they were done, whoopsie, when they were done, what did they come up with? They did come up with this answer here. So don't worry about it, we're not doing it yet anyway, I don't think we do. And then here's another example, but on this one, you've got 2x to the 5th over x to the 3rd. 5 minus 3 is 2. So there are none. There are no. 2 or more, there'd be no. Since this is not linear, it has no horizontal or oblique asymptotes. That's all I need to know. Which brings me back to more my math lab stuff. And none of these will have pictures, okay? It says find the vertical, the horizontal, and the oblique. We're gonna start with the vertical. If you find the vertical asymptotes, you're gonna take the denominator. This has to be simplified. This is already in lowest terms. I cannot reduce it. So I'm just gonna take the x plus 6, set it equal to 0. You'd subtract 6 on both sides. So x is negative 6. It has one vertical asymptote at x equals negative 6. You only use the not equal to when you're identifying the domain. They want to know exactly where is this dotted line. It will be at x equals negative 6. Then they want to know about the horizontal asymptotes, and I put the 5x over x plus 6. I put the function, here's the original function again, all right? This was our original function. I just did a copy and paste so I could draw on it again. This time we are looking for the horizontal asymptotes, and that's when you have to look at the degrees. The degree of the numerator is 1. The degree of the denominator is 1. When the degrees equal each other, then it's the ratio of the coefficients. And my coefficients are this 5 and the invisible 1 right here. So it's going to be what over 5 over 1 is, which is 5. So it has one horizontal, and remember, horizontals are always y equals wherever it crosses the y-axis. And then when I get to part C, the third question, it says, find the oblique ones. Since I had a horizontal one, there will be no oblique. The function has no obliques because it had a horizontal asymptote. All right, and this is number 13. Find the vertical, horizontal, and obliques. So I need to make sure it's in simplest form. This is already simplified. I can't reduce it anymore. So I'm going to take the denominator, and that I'm going to have to factor. That is the difference of 2 squares. That's going to be an x squared plus, plus 4 and an x squared minus 4. But then the x squared minus 4 can be factored to be x plus 2, x minus 2. So I've actually got 3 factors, x squared plus 4. So I would set that equal to 0. Of course, that's going to be imaginary because when you subtract the 4 and you try to square root, you get plus or minus 2i, and that can't be graphed. X plus 2, that means it would be x equals negative 2. And the x minus 2 would be x equals positive 2. So the function has 2 vertical asymptotes. Now, they said the leftmost, that means the smaller of the 2, because you're going from left to right, right? So the leftmost would be the smaller, and that would be the x equals -2. So x equals -2. And then the rightmost would be the larger, and that was x equals +2. Right? Because you're looking at the x-axis, right? And then you've got vertical asymptotes happening at -2 and +2. So you'd have a vertical dash line here and a vertical dash line there, left to right, smallest to largest. And then same function, it wants the horizontal asymptotes. This time I'm looking at the degrees. So the top one has a degree of 3 and the bottom one has a degree of 4. It said that if n is less than m, then it's y is equal to 0. It has one horizontal asymptote, and it is the x-axis. Y is equal to 0. And because it has a horizontal, then boom, on choice C, there's no oblique at all. Because you had a horizontal, you automatically do not have an oblique. And I got 1 minute, but I'm probably going to go over. I'm going to finish. This is my last example. All right. Find the verticals. Well, you have to make sure this is in simplified form. Now, I'm going to show you a little trick. The only way that this sucker could be simplified is if I had another 5x minus 1 in the numerator. Now, my numerator is a 20x squared plus 31x minus 7. If I try to factor that, I have to use that long-ass method, the AC method, and I could do that. But my ultimate goal is to simplify this thing. And the only way it could simplify is if one of the factors of my numerator is a 5x minus 1. So I just put it down there. And then I look at this and I'm like, okay, if this is a 5x right here, what would have to go right here to give me a 20x squared? 4x. And then I look at the other thing. I look at, if this is a minus 1, what would have to go right here to give me a minus 7? A positive 7. And now I just double check it. Does that give me the 31 in the middle? When you multiply your outsides, that's negative 4x. When you multiply your insides, that's positive 35x. And when I combine those, yep, that does factor correctly. And now I can see, okay, that cancels that, which means what this thing reduces to is a 4x plus 7, technically over a 1. That means there is no vertical asymptote, because 1 is the same thing as 1x to the 0, and your denominator cannot be a power of 0. And then I'm looking at, for the horizontal asymptotes, you look at the degree. This is a 2 and this is a 1. If n is greater than, or what does it say? N is greater than m plus 1, or equal to, oh, equal to. If n is equal to m plus 1, which it is, then you're going to have an oblique. And I had accidentally already clicked on this, so there it is. There will be no horizontal. Will be oblique. There's no horizontal. And since it's oblique, I already have the answer from when I reduced the fraction. Let me jump back a slide. It was right here, the 4x plus 7, that is the oblique asymptote. So it has one oblique, and it was the 4x plus 7. And now I'm done. I went over by 2 minutes. Sue me. Does anybody have any questions?
None from me. I'm good.
Cool. Anybody else? All right. I know the schedule says we're supposed to be through 5.4 today. We're a little bit behind, but it's okay. I'll get caught up. So somebody's got a chat down here. What did you mean, Madison? Are you still there? The answer has been under our noses this entire.
Yeah, you said that we've been doing asymptote. We've been finding them the entire time. And
Yep.
I said, Mother of God, the answer.
Sorry. All right, well.
5.4 is not due homework-wise. It won't be due. Okay.
Nope. I'll extend it. Don't worry about it. Just get 5.2 and 5.3 done. And 5.1 if you haven't done that one yet. I think I had already extended those, so.
Yes, you did.
Yeah,
Okay.
you did until this week. So 5.4 will be extended until next week in addition to whatever is already. Okay.
Yes.
Cool.
I'm gonna go in and do that now.
All right. Thank you. It'd be great.
All right. Bye.
All right. See you next class. Thank you for class today as well.
You're welcome. Bye, Caleb.